Welcome to The Explainer. Today, we're unpacking some truly extreme engineering that is absolutely rewriting the rules of modern aerospace. For decades, space flight and high-speed atmospheric flight, they've been separated by this massive barrier of cost and physical limits. But right now, we're witnessing a simultaneous breakthrough in two incredibly difficult areas. I'm talking about bringing massive multi-ton rockets, literally vehicles the size of skyscrapers, back to Earth safely so we can reuse them, and flying aerodynamic vehicles at unimaginably fast hypersonic speeds right through the atmosphere. It's this incredible problem-solution framework combining structural dynamics, advanced propulsion, and cutting-edge AI.
Okay, let's dive into this. Here's a quick look at how we'll break it down today. First, we'll look at the push for reusable rockets. Then check out the hardware actually needed for vertical landings. After that, we'll jump into AI and autonomous descent. And finally, we'll wrap things up out on the hypersonic frontier.
All right, part one, the push for reusable rockets. So the fundamental driver for rapidly reusable launch vehicles, it's entirely economic. Traditional spaceflight is astronomically expensive, mostly because that massive first-stage booster, the part doing the really heavy lifting to get out of the atmosphere, gets completely thrown away after just one single use. As the director of India's Launch Vehicle Center at ISRO put it, the big challenge is, can you bring it back, use its own propulsion to decelerate, and land it safely on a barge so it can be refurbished? That is the primary goal for their next-generation launch vehicle, or NGLV. It sounds simple enough in concept, right? But it's immensely difficult in execution. Slashing those turnaround times and hardware costs by saving the first stage, well, that's the ultimate economic imperative for the future of space programs globally.
To really put this into perspective, let's contrast the old way with the new way. Expendable launch vehicles basically mean total booster loss. Honestly, it's a lot like flying a commercial 747 across the ocean and then just throwing the airplane away after one flight. Crazy, right? Now, VTVL systems, that stands for vertical takeoff and vertical landing, totally change the paradigm because they're rapidly reusable. Now sure, carrying the extra landing fuel and legs does introduce a direct payload penalty. It's usually about 2 to 2.5% of the vehicle's mass. But that penalty is a necessary investment. It unlocks the massive economic gains of flying the exact same hardware over and over again.
Moving on to part two, hardware for vertical landings.
Now, when it comes to the physical reality of actually catching a falling 25-ton cylinder out of the sky, engineers are exploring some really fascinating solutions. They're primarily looking at 3 different leg architectures for a reusable booster: telescopic, hinged, and lattice. And designing these, it isn't just about mechanical convenience. It's all about how these legs handle the vehicle's dynamic motion, crosswinds, and completely unpredictable, uneven terrain during an off-nominal landing.
Well, the data points to a clear winner. After running over 120 simulated landings, sweeping through all sorts of different descent velocities and terrain slopes, the 95th percentile tilt, which basically measures how stable the rocket stays after touchdown, shows that the lattice structure is vastly superior. It actually keeps the rocket stable at a mere 2.1 degree tilt. To give you a mental image, that's steady enough to keep a cup of coffee from spilling on your dashboard. It outperforms the others because it efficiently spreads the force of impact across its many members, using these honeycomb shock absorbers that crush and deform to perfectly absorb all that kinetic energy from the landing.
But here's the thing. Legs alone can't save a rocket if it's coming in way too fast. You need an engine that can decelerate the whole vehicle with absolute pinpoint precision. Enter the SC2000, developed by the Liquid Propulsion Systems Center. This semi-cryogenic engine is a massive leap forward. It pumps out 2,030 kilonewtons of vacuum thrust using liquid oxygen and RP1 kerosene. But the absolute game changer here, the throttle range. It goes from 60% up to 105%. That ability to dynamically throttle the thrust way down to 60% is exactly what allows a rocket to hover and ease into a soft vertical sea landing. Without that deep throttle capability, a vertical landing is physically impossible.
All right, part three, AI and autonomous descent.
So rocket landing control is basically a chaotic physics problem with incredibly limited fuel and absolutely zero margin for error. Imagine trying to balance a pencil on your fingertip while standing in a windstorm. That's the level of difficulty we're talking about with thrust vectoring and vertical landing algorithms. Standard reinforcement learning algorithms often fail at this because they rely heavily on random exploration. So to fix that, engineers developed RAJS, or Random Annealing Jumpstart. It basically uses standard feedback controllers to jumpstart the AI. It guides the system through the initial phase of the descent, and then the AI completely takes over to learn and execute those incredibly complex final maneuvers needed to touch down safely.
And the impact of this AI is just staggering. Listen to this. When relying on a standard baseline PID controller to handle all the insane variables of a rocket descent, the success rate was a dismal 8%. Yeah, it failed 92% of the time. But by implementing the RAJS reinforcement learning algorithm, that success rate absolutely skyrockets to 97%. It's night and day. The AI can process state variables, fuel limits, and aerodynamic disturbances in real time, executing maneuvers that a traditional controller literally just cannot handle. The sheer complexity of these descent trajectories is mind-blowing. The RAJS algorithm calculates thousands of unique, beautiful, swooping recovery paths completely on the fly. No matter where the rocket starts its descent, whether it gets pushed way off course by a gust of wind or experiences a slight engine anomaly, the AI actively calculates the safest route down. It dynamically adjusts the SE-2000's throttle and thrust vectoring to make sure the rocket converges perfectly right at that zero-coordinate touchdown point.
Okay, bringing us to part 4, the hypersonic frontier. Now we're shifting gears to something incredibly fast. Under the highly classified Project Vishnu, India's DRDO has successfully tested the Extended Trajectory Long-Duration Hypersonic Cruise Missile, or ET-LDHCM. Now, unlike your standard ballistic missiles that follow a very predictable arc, this flight profile is a whole different beast. After launch, it kicks on an air-breathing scramjet engine, and because it pulls oxygen directly from the atmosphere, it doesn't need to lug around heavy onboard oxidizers. This lets it hit and sustain a cruise speed of a staggering Mach 8. That is roughly 11,000 kilometers per hour. And it does all this while actively tapping into India's Navik satellite constellation to perform evasive maneuvers right in mid-flight.
This kind of sustained speed turns into an almost unstoppable strategic asset. Cruising at Mach 8 inside the atmosphere creates so much friction that temperatures spike beyond 2,000 degrees Celsius. Obviously, that requires some incredibly advanced thermal coatings. But here's the most fascinating part of the whole thing. Traveling at that speed actually ionizes the air around the vehicle, creating a literal sheath of plasma. And this plasma effect naturally absorbs incoming radar waves, which generates a phenomenon known as plasma stealth. So when you combine that radar invisibility with Navik-guided precision targeting, plus unpredictable low-altitude maneuvering, you've got a system purpose-built to bypass advanced defense shields like the Iron Dome or THAAD.
Which brings us to the ultimate question we really have to ask ourselves today. We are looking at a world where AI can flawlessly land a 25-ton rocket on a lattice leg structure at sea, where NGLV economics makes space access routine, and where scramjets literally rip through the atmosphere at Mach 8 cloaked in plasma stealth. So, how will the convergence of these exact technologies dictate the next 50 years of global security, communication, and the space race? The engineering is already here, the tests are already successful, the frontier has officially been pushed. Thank you so much for joining me on this explainer. Keep your eyes on the skies because the future is moving incredibly fast.